1 plus 10 to the minus 3. It is that's drawn by 10 to the minus 3. Because 378 on the speed of light is 10 to the minus 3.
Okay, sorry Pankaj to kind of interrupt. Actually, so they have to go for this experiment. This transit will happen at that time. So 12:30 they have a strict deadline. So welcome back. So we have Surajit, so who will be basically now talk to you about single disc radio telescopes, mostly focusing on technical part of it. So Surajit, please.
Yeah, thanks. So hello. Am I audible? Okay. Good. So today we will be discussing about the single disc radio telescope. I am sure that already you have gone through some of these details. So if you see a radio telescope, there are some major components of these telescopes. Yesterday Jagdeep already gave you some initial briefing of the structure and all. So if you see that main structure is the parabolic disc. You know why it should be parabolic, not a spherical one? Okay, so circle, I mean sphere also will converge, no? Over a line. So that is called spherical aberration. To avoid that spherical aberration, you take a parabolic surface. Okay. And then what is the next important component is your feed, which you have already made, right? So what is there inside this feed? A dipole, but the most important thing is waveguide, right? The horn antenna. So that is because this may this is not the exact design because they have done it in a two-stage way. But normal design like our GMRT and all, it has only one focus point and there you have the feed, right? So that feed is important because whatever focusing has been done by this telescope, all the signal has to be collected, right? And that can be done by the waveguide because it allows to collect all the signal and pass through that waveguide. And then why you need that dipole? Okay, so why dipole? Why not anything else? So dipole, what kind of power pattern dipole have? Toroidal, right? And if you see, cut it dumbbell shape. So one front is only looking at your signal, right? That toroidal, because maximum sensitivity or collecting efficiency is the surface of that toroidal or peak of that, right? If you cut it, then you have a kind of circular kind of thing. But why that dipole? It could have been monopole because monopole has the directivity, no directivity. Everything it can collect, right? If you give a dipole, it may not collect everything because it has a 45 degree or something, your WHM of that. Huh? So why it is dipole, you know? You know radio signal has a polarity also? So monopole does not have that capability to detect the polarization because it does not come on a plane, but a dipole can do that, right? So GMRT earlier had two different this thing, I mean two dipole having two different frequency detector. So they are placed like cross wire kind of. Okay, fine. So there you have the dipole as a detector, right? And dipole converts your whatever that signal to electric signal. Then what there should be? because this signal is very, very faint. Now, if you collect it and put it in your wire to take it to your data center or whatever, what will happen? So it will loss. There will be a huge loss and you may not get it. So immediately you put a low noise amplifier at the feed itself. So that will amplify the signal already, and then somewhere through coaxial cable, somewhere through optical fiber will have less loss. Through that you take out your data to your data center. So there you will have the receiver and further amplification and all this stuff will be done. I mean, those technical things will be possibly learning in the lab itself. And then computer will be there to store those data, and later on you can analyze those data. So this is the basic structure of the single dish radio telescope. And what it does is that, there is another system. This is mounting and tracking. It could have been just focusing on one point, but you need to track the source because you need the integration over that. So your antenna should track a single source for longer time to get a better image. So that system is also there. So what kind of sources it detects? Again come to that point. Which kind of wavefront it is focusing? Is a parabolic dish. Which kind of wavefront it is receiving and focusing? Non-wave, so parallel waves, fronts. From where you can get that parallel wavefronts? Distant sources only, right? So it detects your all kind of astronomical sources which sends the parallel rays. Okay, fine. So these are few example of famous single dish radio telescopes. So this is Greenbank in USA, which is around 110 meters. What is the size of GMRT antennas, you know? 45 meters each. And okay, so then you have this one as 76 meter or so. This is 100 meter, and this is something 64 or 65 meter telescope. And we have a 45 meter, but we have lot of like array of telescopes. Can you see another thing? I mean, first thing is that it has a large collecting area because around 100 meter. Actually, there were another one 300 Effelsberg and China has a 500 meter fast. So those big telescope, a single telescope, what you get from it? Lot of photon collection in a single dish, right? Okay, so your sensitivity will be very high. Then these are fully steerable, but the China one is also because they steer the feed in a different manner so that they can focus on that surface, various surface, and change the position of the sky to which it is looking at. Okay, and if you see, another thing is multiple bands that it can observe. That is also true for arrays like GMRT, which works as single as well as array, but GMRT has feed, it can be rotated. Okay, in 2 axes it can be rotated, so total 4 feed they can, at a time they can put there, and only by giving command they can change, rotate it to a proper feed. The frequency depending on which frequency you want to observe. And that is also true for single dish antennas, so that is done. But another technique is there. You see that some are solid and some are mesh. right? These two are mesh kind of design and these are solid. So what will be, how you can have mesh kind of this thing, all the signal will pass through? Okay, so okay, so mesh size will be depending on that, and GMRT has smallest wavelength of smallest wavelength 21, no? L band is the highest energy band. Others will be longer, so that does not matter. So 20 centimeter and GMRT has mesh size of 2 centimeters. So it is kind of greater than. So you can use it. I will give you an example. Sometimes we call, this surface is very smooth. Okay, so what goes in our mind, why it is smooth? Yes? Huh? What? Less irregularities, but how we determine the irregularities? Why it will happen? No, what is the factor that you have to take care of? See, yeah, I can see this thing with scanning tunneling microscope, right? It will look like a hill. Huh? So, what the factor that you should take care of? So, roughness of the surface should be much less than the wavelength at which you are looking at. The same thing here it is happening, right? Okay. So, roughness means mesh size gives you the roughness, and that should be smaller than the wavelength at which you are observing. Okay, so let's take a look in the, which we many times actually experience. These are some kind of image production basics. So what is this? You remember when we were child, we used to make this pinhole camera in a box, a small hole, and on the other surface we put a white paper or so, and we could see the image there. But it will be inverted. What is the basic physics there? You know? So light travels linearly, right? In usual circumstances. And why a pinhole? No, it's not diffraction. Yes, so you are telling something? Okay, fine, it's not really comparable to wavelength, but there is something to it. But thing is that comparable to wavelength means you will get diffraction. So here diffraction should be very less actually, otherwise image will be destroyed. So what happens is that you are allowing to pass only few light rays, just 1-to-1 correspondence as he told. So those lights, the light that is coming from there is falling here and this. So you are not allowing much of the photon or light to pass from the same region. Okay, that's why the pinhole is. Okay, so that is one kind of image production technique. Now if you see our own eye, it's a, what I can say, it uses multiple techniques. The same thing happens, it has a pinhole and it allows the figure to form in inverted manner on the retina. Then it has a lens also. What it will do? More focusing means more sharper image you get. And the pupil has an aperture, right? And that will create a diffraction as well. So it is the diffraction technique of image production is also used there, but this diffraction also restrict us from looking at much smaller object because there is a diffraction limit. So what happens in case of radio telescope, it uses the diffraction technique. What the diffraction is happening? So, what you know about diffraction from your bachelor's classes? Thanks. Fine. So what do you do? What kind of source you will take? Monochromatic, so it's a laser. Why you need a laser? Okay, coherence and all will come later. The first thing is, it is important, but first thing is what kind of diffraction we are talking about? Fraunhofer, right? Yesterday you had that discussion. Fraunhofer needs your light to be or source to be at infinity. In lab you cannot create that, right? You can. So you should use collimator and then lens to make it parallel and all. But if you use laser, you don't need to do that. So you are using a laser here, and here your screen is also at a local place, not at infinity. How it is possible to use? Because Fraunhofer, actually if you place it this much at this much distance, it's not this much, 1 to 2 meter distance, still it works. You will see your diffraction pattern here. Why you get that? Okay, it should be very small. That has another reason that I will come to, but apart from that, this is D. Let's say this is D, and your wavelength of the laser is lambda. So usually it will be optical wavelength, right? It's in nanometers, and you are talking about few meters. Okay. So it's apparently, if you put a lens, you will get much sharper diffraction pattern. But if you don't put a lens, still you will get, because it apparently like a long distance. Because you are comparing your wavelength to that distance. Now tell me, what kind of aperture this is? An order of wavelengths, fine. But what kind of means? What is the geometrical shape or mathematical shape of that? No? That I will come to. Now we are in Fraunhofer diffraction. I'll come to that later. So here it is a or the opposite. Right? Okay? you can represent that as this function. Okay, and what is the Fourier transform of this function? Sinc function, and what you get here is sine beta by beta, sinc function, right? So it's a Fourier transform of the it's not delta function. If it is delta function, what will happen? What is the Fourier transform of delta function? Constant, right? Okay, fine. So you get this is double step function, so rectangular barrier kind of. Okay, rectangular barrier. If I put a barrier, what will happen to this? Instead of opening, if I put a barrier, what will happen? So barrier means you have a block here and you get your two diffraction pattern both the sides. So opening will give you in the central region you have the central peak and then the side lobes. Fine. Now if I give a square, that means from the surface I can see another thing, why this should not be much more than the lambda. Someone told me it should be around lambda. If I increase this width, what will happen to your Fourier transform? Okay. Okay, so got it. Now if I have another side also, how it will look? It will look like you have central, then a smaller square, then this thing, both the sides. These are square. So you will get the diffraction pattern like that. Okay. Now if it is a circular, okay, so now you got it. Now you have here in your telescope, you have a circular aperture, right? The whole telescope surface, you are cutting it, that parabolic disk, you are cutting on the surface, right? That is the aperture that your incident light will see. So it will create a sinc function, but sinc squared, it's a power, right? Intensity, you are squaring it. So that's how you get this thing when you are cutting it in 2D. And if you see, the central one has the maximum, then it diminished almost by 95% actually, the height wise. Then 1% or so. So it goes sharply down in further peaks. And then the central thing is called the Aries disk. You know how to, when you call something resolved, so the hub maxima should cross over, right? 2 point source, it won't remain as point source because it is a diffraction. Your point source you see as a Aries disk. So 2 Aries disks should not overlap much more than the your hub maxima. Okay, fine. So now you see the beam pattern. What we have done? The same plot actually we are plotting here. All engineers uses the polar plot, right? And even your bachelor's, if you have optical practical, you also have done that polar plot. The same plot, this I am plotting here in polar plot. What is it will show? It will have a central lobe and the side lobes, which is slowly diminishing as it goes to 360-degree and all. So your main lobe has the most sensitivity. Again, yesterday Jagadip told that reciprocity, right? Its power pattern means it absorbs also more in that direction. And you have the then side lobes and all. In radio astronomy, these side lobes are killer. Okay, so they create various kind of confusion noise, contaminates the imaging process. Okay, and okay, so already we covered this. One more thing is that this Aries pattern is a theoretical one, but in reality you will have various kind of deformities in the your dish, and feed illumination means how much signal you can pass it to your feed, and those may not be 100%, right? So actually if you theoretically calculate the area that is you are collecting is not the exact area in practical sense, right? Those losses will be there. So now think about how this antenna sees or collects the data. One parameter is called the gain. That means at a certain direction, what is the efficiency at which it can collect the information. So that is defined like this, where your A is the physical aperture, which you can just calculate theoretically. And you have a efficiency factor of aperture efficiency. I'll come to that point. Before that, all other is, it depends on the lambda as well as, okay. So these are the thing on which your directivity gain depends. And if you see, this eta is nothing but the the maximum possible collection that it does because of various factors that already we talked about by the geometrical area of the disk, right? So this is the efficiency factor, because if it is ideal case, you get this. This happens because the antenna itself has some cutoff on the Aries pattern that you see, and it cannot collect all the signals at various directions. The next thing is that now the effective area already I talked about. If you want to put it in figure or in calculation, it looks like this, and that determines your power that your receiver receives. And if you see, that power can be converted to your flux, physical flux. Before that, there is another thing, because till now what we are dealing with is some voltage, some signal, which is not directly related to your physical flux. That we will come to. What else is there? Already we talked about resolution, how we compute resolution we talked about, but what is the value for that resolution is the size of the Aries disk. Okay. So which is roughly calculated to be 1.22. It depends on lambda and the diameter of the telescope. Okay. What else is there? However you make a perfect instrument, it will have various kind of noises. Okay. It's an electronic active circuit. You will have heat, you will have lot of other things. So this T system, we express it as temperature, but it is not really temperature. something called Nyquist theorem, which converts your voltage to temperature. It's not directly related to temperature, but you can relate. Like you create a circuit, pass some voltage and all, it will heat up, right? So it's kind of that analogy that we are taking, and we are calling this as the system temperature. What it includes? Your sky has a background that you calculate as temperature. Receiver itself produces some kind of noise that you calculate as receiver temperature. Some spillover is there which you are not able to collect. That gives a noise, adds to noise to your collected signal. And ground, there is ground pickup also. Because like G-battery, which is a mesh, it can pick up more ground noises in that sense, because it is not fully insulated. So that whole temperature will help you to calculate the theoretical noise that you will get from your telescope. What is that? This is the total noise. But you can overcome that noise by, this noise is dependent on one lambda. If you increase your bandwidth, the noise will go down. Yes, you are collecting more data in that sense. But that is root over. It's not directly proportional, root over. And the time, as you integrate more and more, you get. Well, that there is a reason for that also. Like most of the noises are random, Gaussian kind. So if you integrate it, your noise level goes down. Okay. Now from all this, now you can calculate the brightness temperature, because already you have calculated S somewhere, and now this is the formula, because this is the total your solid angle that your antenna substance, and this temperature is, this is energy actually. So from that you can calculate the, it's opposite, you are getting the brightness temperature from flux, but you can calculate, if you have the brightness temperature as a parameter, you can calculate the flux of your system. Yet this flux is not exactly the physical flux of the system. I will come to that point when I talk about how to image using the single dish radio telescope. Okay, so now for a point source, earlier a theoretical RMS calculation we have done, that can be used to check that what could be the minimum flux from a point source that you will be able to detect with your single dish radio telescope that you have made, which is given by this. All the parameters already you have described, and from that we can calculate this, that what will be the minimum flux from a point source. If it has, we can detect with your antenna that you have designed. Now going into the image processing. So we have created our telescope. We know all the parameters in our telescope. So how to image? Now we have a telescope that at a time can point into one position. Okay. And that is also restricted by the beam size. That point has been seen by your beam. So what you will do, that first you are pointing it at some position. Then what you will do, that start scanning. So you create a grid. You create a grid and you determine that grid positions. You move your telescope to that next position. Like that you can scan the whole region that you have defined. It's a graph paper. Each grid of the graph is one point and you are moving along some line. You can like scan it in a one line, line by line, or you can move it like this, whatever way. You do it, at each point you go and keep your telescope for certain time. You keep it for the same kind of time interval. You give for same time interval, so that the background for each of the point does not get different, and each places you take the data out, record it. So now you have collected that data. So this will form a image grid, but these numbers that you have stored is not a real number, right? It's not real flux because we have not calibrated it. What we got is the voltage from our telescope, one signal, whatever number you tell, that is not calibrated. And calibration means also it changes day to day, time to time. So before each of the observation you have to calibrate it, or you take a standard one which is calibrator source and you observe it and weight it with that factor, because now you know that your telescope gives this much signal from a standard candle. So you can take that as weight and get individual point, flux at individual point. If you do that, what you can do is that another thing is remaining till, that is this may be the intensity at that point in the sky. Theta phi is your sky position. This is the real intensity of your object. This is the observed intensity after all other calibrations. Still you have something called the beam pattern. Beam pattern, already we showed that that can be expressed as a beam pattern again in the theta phi. So beam pattern is convoluted with the signal, real signal. The signal that you are getting a convoluted signal. You have to deconvolute it to get the real number, right? Yeah, so already we talked about those calibrations, and now you have that each point you have the data or number, real number. Still various contamination may be there, that is the error or RMS that will take care of, but you get that. Now you can plot it on that graph, and if it is not a point source, if it is a point source, it will be in one beam size, right? It's not on one graph point, but it will be within one beam size. But if you have an extended source, then what you can do? Each point you are writing the number, right? Then you know that you can create some kind of a contour map. You take some number that if some grid point is above that, I will put a line in that, you get a contour map. That's how you create your radio image. Okay, it's not like optical, right, where you get the direct image, direct photon number and all. Here, this is how you make your image. But this is your single disc radio telescope, which has some pros and cons. What is the advantages? Because we can create a large telescope, you have a large collecting area, so your sensitivity will be very high. So you will be able to detect very faint sources. Then calibration is simpler, because once you take your array, you have to think about the phase matching and all these things, because all will not be detecting the same photon your light at one point in time, so you have the delay time and phase matching, all this stuff, which is not there. You are simply pointing to some position and you are getting the value. Multi-band, yeah, fine. This is not only in single disc. In array also you can do, but single disc people traditionally doing this. And these are very highly sensitive, so if I have one in India, I can collaborate with China or USA to make very large baseline array. Okay. Very large baseline array means that lambda by d. If d is going very high, you get a high resolution image. So that you can do. And full sky accessibility, you can one telescope only, you very freely move it and scan it. And these are some field where they very often use it is the pulsar timing and spectroscopic studies. Because those needs very high sensitivity. They don't need that kind of resolution, but high sensitivity is paramount. So they use this kind of telescopes. Now limitations. You see that this, so your angular resolution will be poor. So if you want to resolve your source very much, this is not the one. Because if you calculate a 20 or 30 meter telescope or even 100 meter telescope will give you few minute of resolution. Whereas geometric gives you 2 arcsecond resolution at L band 20 megahertz. Then large physical size, and again you will be moving it and all, those are very costly technology. So that also negative point of that. And RFI, because high sensitivity, little bit of RFI if is produced around the region, it will be affected. Now you have only one dish. When you have multiple dishes, you can throw out some of the dishes. Here you can't do, so that data will be lost. Then single beam limitations, again the thing is, it is time consuming because the imaging technique I told each point you have to go and get that thing, which is not the case in array. And yeah, so resolution is poor, the same thing in a different way it has been presented. So this is how the single dish radio telescope works. Yeah, so.
Locate right ascension and declination of like whatever source we are observing using a single dish?
Okay, so there is this GPS fixed to each of the antenna, and you have to calibrate it obviously. Every time the observation is done, before that the pointing calibration is done, and then they fix it accurately. But use of GPS is there. Naren, right?
Yes. So basically, if you know the array and date of the source, so given that time,
We can
you would know that what is the azimuth and elevation
elevation.
you will be required.
And if we don't know the
So if you do not know, what people do is that I know the alt and azimuth, right? I scan the sky with a single dish radio telescope.
okay.
Let's say. So I scan here. Every time I'm just pointing this.
Okay.
So if I detect some source over there, then I exactly know that what array date was there, what time was there, what latitude, longitude we were doing the observation. From there I can calculate what will be the array day contact.
Okay.
That is how the unknown source was detected, and you map a sky, so you see this capability.
Your local position is determined by the GPS.
GPS. Okay. Yes.
So when you're talking about the contour plots, and there is also mentioned that false heat maps. What are those?
False?
False heat maps.
Oh, what was that?
Yes, yes, that's right. Last one.
Oh, acha. It's a color map. Heat map, you know, right? To define some success and failure, we put a graph for, first we divide our problem into some grid positions, and each grid we define some number for success or failure. So that is heat map. The same thing you can do, that you define a color bar for your flux. Because optically you have a color, but radio you don't have the color. What you can do is that, let's say your source is varying in the flux range of let's say 1 millijansky to few jansky. The whole range you divide into some colors, and each color you put a false color there. So it will look like, okay, highly powerful source somewhere, and somewhere it will be very faint. Yeah. No, space has no RFI. RFI creator are us. Okay, so first of all, that region where we are putting our telescope is chosen to be quiet region, less RFIs. But if RFI come into your data, then the problem comes. Sometimes you need to, because RFIs are very distinctly visible, right? Distinctly identifiable, because it will have, because RFI is terrestrial thing, and the signal is very high. So if you take, let's say, 5 times or 10 times the average signal at that time, beyond that, that will be surely a RFI. It won't be a terrestrial source. So you remove that. For the time range for which it will be there, for the, okay, here no baseline is there. So for time range that you get that RFI, you remove it from your imaging. And there are other ways also. What you can do is that you downplay those. You detect them, you weight them in a lower manner. When while imaging, you put them in a lower manner, some 0.001, with that you multiply, something like that. With that you can remove this RFIs from your source. Any other thing, Naren?
No, I mean, yeah, so that is the basically, I mean, there is no cure.
It will be there.
Frankly, okay. So typically what observatories do, that they try to locate the source of the RFIs. So GMRT, for example, has a dedicated team for RFI detections, and they try to mitigate them. For example, earlier days, GMRT, people used to have this Yagi antenna and look for the source, and they realized that this tube light, now this LED has come up, and that earlier this, tube light is dab 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 karke phir jalta tha, right? So the choke of that actually creates problem. So then they actually replaced in that surrounding area, surrounding villages, all these tube lights by this. Then they used to have this CFL lamps, okay, CFL thing. That is one. Then they have also done, for example, this power lines, this 11,000, this high tension power line goes, right? So if this insulators,
Okay.
insulators are bad, okay, insulators dekha hai na, this iske is a circular as a, so yeah, so there some discharge happens. If these insulators are not good, then there will be some discharge and there will be some sparks. And apparently these sparks, even if you may not see it, they radiate broadband emissions. Okay, so these guys actually located all of this, and they have replaced all this high tension power line around GMRT with a better, higher set of insulating this thing. Okay, so these kind of things has been taken. In fact, there was generator. Then there has been lot of fighting with Geo. So Geo had
removed their antenna.
yeah, so they had this GSM band at 700 megahertz or so, around 900 megahertz. Okay, so which was creating a lot of problem, and they also have a band at higher frequency like 1.8 gigahertz and so. So then they have lot of negotiated, and then told them that why you won't need this band. Okay, go to 1.8. It's creating problem. So they have done that. Air Force, another problem. So sortie the Sukhoi M30s, okay, around GMRT area, and their communication was actually coming exactly same band what we used to observe. And army is very difficult, so they don't believe it. So then we called army guys, sit here, do your duty, we'll show you. And then they have actually said, okay, fine, we will not come in this side, we'll go on the other side. So yeah, yeah, there are a lot of problem, and RFI is a killer. Yeah.
Sir, I have a doubt in the calibration part. So, if there is some incoming radiation and it is sort of attenuated due to some weather loss or something, so how do we restore or resolve it computationally? Like, I don't know.
Attenuated in what
Maybe
sense?
because of weather condition or maybe rain droplets or something. So how
Okay, I don't think that these bands are much affected by the rain or cloud.
Okay.
It could be little higher. It's not communication band, right?
Yeah, but I mean, sometime, but there is a way people have characterized that what is the time scale, for example. Amplitude does not get perturbed so much, but phase do due to the ionosphere.
Yeah.
So what you
So
do
that's
is
the
that
difference.
you observe a known source every half an hour, and you know that within half an hour things are not going to change. So then, like this calibration process, if you the next week we will do some data analysis, you will see the calibrators are observed like every half an hour or 45 minutes. That is because the ionosphere and the other the conditions, atmospheric condition you are saying, they are not stable beyond like 1 hour or so. And if you go lower in the frequency, that's again the ionosphere problem is more kind of severe. Also, if you look at higher frequency, like 100 gigahertz, 200 gigahertz, so they are like the wavelength is getting shorter, like going towards microwave, and microwave do interact with water. That's how you heat your food, right? So atmosphere has water, and this water content actually keeps changing very fast. So if you see the high frequency telescopes, they actually do this process even more often. And this ALMA telescope, if you see, it is actually high altitude and in desert. Why do you think that people had to go there? So this is another reason. So yes, it do affect sometime, but then people figured out calibration processes to observe calibrator more frequently. Yeah. More questions? Some people are sitting idle. Actually, I am noticing. They will be caught next time. All right, okay, so thank you, Surajit.
Thanks.
So, as a token of appreciation, I would call Ankur to hand over a small gift to, okay, you are a cameraman. Okay, yeah, he can take the photo. Ankur, you come. Yeah. Yeah, so our volunteers actually working very hard, so, so okay, so thank you. So we break for now, break in the sense that you will be going upstairs for this H1 observation from the galactic plane. So the experiment will take place in per balcony. So if you can follow me, Sangeeta and all the other volunteers will also be there to kind of take over your experiment. And we'll have the experiment session till 2 o'clock. We'll try to clear it earlier. After that, we'll have lunch, and after lunch, we'll have the final talk today by Professor Petra. Right? So, follow me or Kirti, and we'll take you there.
You can keep your bags here.
Keep your bags here.
So you people are just doing the observation, then you will go to lunch and come back here. So keep your bags here. No. No, you don't need to carry.